Hey everyone, today we're going to wrap up what we need to be able to do with the fundamental theorem of calculus. This will be our last new material for the chapter. The only other video we'll have for this chapter will be going over some AP type questions. So like I said, we're going to keep working with the fundamental theorem of calculus. Before we talk about the new stuff, we're just going to review some basic problems using the fundamental theorem. Okay, so for number 1 and 2, our directions are to find dy dx. And so now the basic idea, if you remember with the fundamental theorem, is that if we're finding the derivative of an integral, we know that those are inverse processes. So essentially they're going to cancel each other out. So for number 1, if I want to find dy dx, that's just taking the derivative with respect to x of this integral from -2 to x of the square root of 1 plus e to the 5t dt. And remember, we said we have these dummy variables here because we don't want to match the limits of integration, and that'll be really important today. But remember, with what we've done so far, we said as long as our lower limit is a constant and our upper limit is just x and not a function of x, when we take that derivative, all we're going to do is substitute the x wherever we see a t. So to find that derivative now, it's just going to be the square root of 1 plus e to the 5x. And that's our derivative. So all we did was take our x and substitute where we saw the t. So again, when we have a lower constant limit of integration and the upper is just x, it's just substitution. Now, number 2 is different because both of my limits are functions of x. So remember, this is going to require some use of the chain rule. So now, when we find our derivative, essentially what we're going to do is we're going to evaluate this at the upper limit, and then we're going to subtract the lower limit, but just remembering we need some chain rule. So for the first round, I'm going to do cosine of 2 times my upper limit, which is x cubed. And then we're going to multiply by the derivative of x cubed, which is 3x squared. And then I'm going to subtract. I'm going to do the same thing, but now with the lower limit. So I'm going to have cosine of 2. Now for t, I'm going to substitute my x squared. And then I'm going to multiply by its derivative. So my derivative is 3x squared cosine of 2x cubed minus 2x times cosine of 2x squared. So that's a really quick review of the fundamental theorem. So now what we're doing today, the new piece, is we're going to use the fundamental theorem to help us construct a function. Okay, and just like it says in the notes here, the fundamental theorem is going to really help us to solve differential equations when we don't know the antiderivative. That's when this is going to be extremely helpful to us. So here's how it kind of works. So our job is to find the original function, y of x, if the derivative is tangent of x, and we have our initial condition, f of 3 equals 5. Okay, so here, just to make a few notes, here's our differential equation. Okay, I recognize that by the dy dx. This one is not separable. It's just in terms of x, so it's pretty basic. And then here, we have an initial condition. So if our differential equation, if this were easy to antidifferentiate, this would be a pretty easy problem. But we don't really know a function whose derivative is tangent of x, so it makes it trickier. So here's what we want to do. I know if I wanted to solve this differential equation, I would need to integrate tangent of x. So I'm going to put my integral. I know I'm trying to find my function y of x. So if I were going to solve this, we know that we would move our dx over to the right, and then we would have to integrate both sides. So I would have the integral Now here's where we want to be careful. If I move this over, I would have tangent x dx. But we need to use that dummy variable like we were using in the examples up here where we had t in our integrand. We're going to do the same thing down here. So instead of tangent x dx, I'm going to put tangent of t dt. Okay, so the interesting thing now, the thing that's going to be different, is our function is actually still going to have an integral in it. Now, here's what happens. Our x from our initial condition becomes our lower limit of integration, and the y value is a constant that we add on to the end. And our upper limit is just going to be x. Now let's check that this derivative is actually tangent of x. So I'm going to do a check step here just to show that this works. So we said our function is y equals the integral from 3 to x of tangent t dt plus 5. So now let's differentiate this with respect to x. So dy dx is the derivative of the integral from 3 to x of tangent t dt plus 5. Right? So we're differentiating this whole thing. So now, really what we have is the derivative with respect to x of our integral from 3 to x of tangent t dt, and we have the derivative with respect to x of our constant 5. Now, this should be very familiar here. This derivative of an integral, that's just the fundamental theorem. Right? Since my lower limit's a constant and my upper limit is just x, to find that derivative, we just substitute x. So now I get tangent of x. I know the derivative of a constant is just 0, so my derivative is tangent x, which is what we needed. So that checks out. So that's how we're going to form these functions. So let's go ahead and generalize it a bit. So if our derivative is f prime of x, and my initial condition, let's say y of a, so my x value is a, and my y value is b, here's what our function is going to look like. It's going to be y equals, it's always going to include an integral. That lower limit, or my x value, becomes my lower limit. My upper limit is going to be x. I take my function here, but instead of using x, I'm going to use my dummy variable t, and I put dt, and then I'm going to add on the y value. That's how we're going to construct these functions. And so once you learn the pattern, they become very, very quick problems to do. So let's go ahead and look at some examples. And again, the purpose here is just doing this when we don't know the antiderivative of a function. If we knew the antiderivative, then we could just solve this like a regular differential equation. All right, so here we go. We're going to construct a function y equals f of x with the given derivative and function value. Sometimes you might see the directions a little differently. They might say solve the initial value problem using the fundamental theorem of calculus, or I'm just going to say the FTC. So it's a couple ways you might see the directions. But either way, what we're trying to do is really solve this differential equation. So for number 1, my derivative is this. Here's my function. And obviously, I don't know very easily, I don't have at top of mind what the antiderivative of this function is. I just don't know it. Okay, so I have a function, and then I have my x value, my initial condition, and I have a y value of the initial condition. So here's what our function is going to look like. It's going to be y equals, we're always going to have an integral, and the upper limit is going to be x. We said our lower limit of integration is our x value. My function comes from my derivative here. The only thing I do different is I use my dummy variable of t, so cosine squared of 5t. I use my dt to close that integral. And then my constant comes from my y value, so minus 2. And that's it. That's all you need to do. That would be our function. Okay, so we're just going to run through a few more. Okay, so here's my derivative. That's going to be my integrand with a slight change to the variable. Here's my x value, which I know is going to become my lower limit of integration, and my y value, which is going to become that constant. So now I get y equals, again, I have the integral. The upper limit is going to be x. My 5 becomes the lower limit. My integrand comes from my derivative, so sine cubed of t, and I close that with dt. And in this case, I could add a plus 0, but that's not going to change anything, so I'm done here because my y value was 0. Okay, at this point, I would recommend pausing the video and then unpause it to check your solution. Okay, so here's the solutions to those last two problems. Just a note on notation. Please be sure that you always have your dt here to close out your integral. So when you have an integral to open it, I kind of treat these like parentheses, the integral at the front and the dt at the end. So you'll lose points for notation if you don't have that dt. Also here, since this was dy dx, I named my function y. You can see here, since this was f prime of x, I named my function f of x just to be consistent with my notation. So like I said, this is the last new material for the chapter. The next video will go through some AP review, and then we'll be looking at our test for this chapter.